Good afternoon. I'm Nuno Carvalhais. I'm here to present the results of the BioMASCAT project. This is a project that was initiated by Mauricio Santoro and I a couple of years ago, and that involved a close collaboration between our team in the Max Planck and Gamma Remote Sensing. The main purpose of the project was to develop a long-term time series of above-ground biomass data sets, mostly relying on legacy data from old C-band scatterometer data. We wanted to start since the early 90s until as much as possible present. And we wanted to look into the data that we could derive and understand what would be the links to the carbon cycle challenges, mostly carbon cycle science challenges. This was a project that was funded by ESA under the EU for Society initiative in scientific data exploration. So the BioMASCAT algorithm is strongly based on the Biomass SAR algorithm that has been mentioned before by Oliver, and that basically relies on the inversion of a couple of structural parameters using the water cloud model. And the advantage or the developments that were done in context of the BioMASCAT was the extension of the algorithm to use additional data sets about forest structure that relate to height via LiDAR, to canopy density, also considering land use and land cover data sets, so that many of the terms of the water cloud model could be inverted as close as possible to observations at the same time that would leave free biomass, and that would be basically inverted using the scatterometer data. And one of the this algorithm has just been published in Remote Sensing of Environment last week. I think you can already find it easily in the website. And one of the strong efforts that was done in the context of the project was actually to dig and combine, harmonize legacy data sets from WinSCAT, ERS1 and 2, MetaPascat, and Visata SAR to actually combine and make this long-term time series. So in the end, what a first product that came out was this long-term time series, almost 30 years, from 92 to 2018 of global coverage, quarter degree with an annual temporal resolution and associated uncertainties. And one of the things that we started immediately thinking of was how to look at global dynamics and also the spatial distribution of global dynamics using these data sets. So one of the first studies that we came out with was led by Simon, where we looked at the changes in above ground biomass between time steps and associate that to the NABP, basically the net above ground biomass productivity that we could find for every grid cell, and try to associate those changes or those time series to different aspects of ecology that we know of. So what we would relate there would be to growth and allocation mechanisms that speak to primary productivity and to allocation, and at the same time associate also to it loss terms as background mortality, disturbances, or management practices that will lead to actually harvesting, things like that. So once we look at the net gains and losses, we have a perception of very small at the global ecosystem scale. So basically what we're talking about is landscape scale statistics of like 25 by 25 kilometers, but that reflect losses, for instance, in the Inches of the Amazon or in the Congo Basin, some in the Central East Asia, as a net change across these 30 years. Once we start looking at in relative terms, these are actually small compared to actual biomass that is in those grid cells, but it's actually in the spatial distribution and temporal dynamics of these changes that we find very interesting information. For instance, here we contrast the AGB class, which is basically a proxy also for age, with the actual absolute changes. And once we look at it, we see that stronger absolute changes are smaller from smaller classes to mature classes, and then they reduce again. If we actually look at it from a percent or relative point of view, we see that we find the highest changes, so the highest growth or the highest increments, but also the highest losses for younger forests or for less developed forests, and that starts decaying. And this tendency to have like a less percent change with higher stock is also something that refers directly to forest ecology and dynamics of forest demography, as it's coming from ecology and demographic principles. Of course, we start looking at it from a grid cell perspective and looking at different covariates and understanding that, for instance, if we look at vegetation type of variables, like the change in forest cover, the proxy for the state of development of the forest, like the AGB of the LAC2 or primary productivity. Once we look at change in forest cover, we see a very monotonic and positive relationship between change in forest cover and biomass, which is something that we're expecting, and it's very rewarding. But once we start looking at the variation with vegetation variables, but also atmospheric variables that speak to productivity or to growth or decay conditions, the correlations are not homogeneous across the globe. And actually, if we start partitioning that in terms of very large groups of variables, we start seeing that, for instance, atmospheric variables have a very strong role in terms of temperate and also tropical regions, and that vegetation variables start having more or show more importance or dominance importance in terms of very wet forests like in Brazil, but also in border regions like we see in Southern Africa. But water is actually something that manifests most of a dominant role in semi-arid regions, which is something that is very obvious, but to have it as a first cut on an observational data set is something that brought us confidence in the data that we're looking at. You start thinking then, what are the links that we can establish between this data and the global carbon cycle from completely independent variables? So we looked at atmospheric inversions that basically infer the land surface or the land carbon sink from atmospheric measurements of CO2 concentrations in time, distributed in space in this case. And we see two different aspects in terms of correlation. One of them is that the long-term mean in the sink capacity of the ecosystem as it emerges from the BioMASCAT product correlates very well with the estimates from inversions. It's not perfect. We have a couple of, or we have at least one outlier in the relationship here, which speaks to the Central East Asia region here. But in general, there is a very strong agreement between the spatial variability or the long-term mean in the land sink and the long-term changes in the net above ground biomass productivity. We see the same thing in terms of interannual variability when we just contrast directly the standard deviation of the inversions with the standard deviation of the NABP for these regions, which actually led us to a little bit valiant establishment of a relationship between the CGR once we reduce the fossil fuel and the ocean fluxes from it, and the BioMASCAT data set. And one of the things that we appreciate when we look at this figure is that interannual variability in most of the years correlates very well or is associated very well between the BioMASCAT and the CGR, or the land carbon sink contribution to the CGR, but that's not ubiquitous across the time series. So we have a couple of puzzles here that speak to either missing mechanisms. Of course, this is not a complete mass balance, but either they're speaking about very dominant missing mechanisms in our relationship that are prevalent on those years, or we're talking about understanding a little bit confidence in the data set for each individual year that is bringing a little bit further the distance to this time series. So I think I'm going a little bit beyond time, but I would just like to also offer this perspective.
Time to conclude, maybe.
Okay. So, Philippe, one slide on just like explaining that we can also look at this data to contrast the speed of the carbon cycle at local scales between traditional steady state assumptions and non-steady state assumptions. And what we're actually observing is that at global scales, these relationships still hold very well, but locally, especially in transition regions, these are not really common. And depending on the scale, what we're actually seeing is a systematic underestimation on the speed of the carbon cycle on the land surface that we can actually diagnose now with this data set. So overall, I hope I presented a new perspective on a data set that we've been building that has brought a couple of insights in terms of forest ecology, but also in terms of like the global carbon cycle. And I don't want to delay any further. And I thank you very much for your time.